Okay, so let's talk about hypothesis testing. So hypothesis testing is sort of a natural continuation of confidence intervals. I can't have you guys up at the same time, so it's sort of a pain. All right, so I'm going to go through this spreadsheet and just hold your questions until we're through it. You can pop in with an audio question. So we're going to just talk about hypothesis testing and means. So you can use a hypothesis test to test a whole bunch of things. Here's an example. Dog breeders claim that every Dalmatian has 35 spots. You get samples from a whole bunch of Dalmatians, and you can test that claim. You can also, let's say there's a claim that 85% of community college students are on Facebook. Well, you could collect data, and you could test that hypothesis or that claim. Just like we could find data on the mean age of QCC students is such and such, we could go out and collect data and test that claim. So there are three types of hypothesis tests. There's a left-tailed hypothesis test, and that's usually when your H0 is either the H, you're trying to test that the mean is actually less than what it's currently stated. And in hypothesis testing, we talk about sort of the mu is what's currently accepted. Okay? So in a left-tailed test, you are claiming that, let's say the mean age of TCC students is 24. You're claiming that you think the mean age of TCC students is less than 24. It can be written one of two ways. It's always a statement of equality. So H0 will always have equality, the equal sign into it. Sometimes people will write it as H0 is greater than or equal to mu, or H0 is equal to mu. Both of these are sound, but the alternative, H alternative, is always less than mu. And in terms of a left-tailed test, you're testing to the left. So your shaded area is to the left. In a right-tailed test, we might want to claim that the mean age of TCC students is greater than 24. So our H0 would be that mu is less than or equal to, or just mu is equal to 24. And the alternative would be that it's greater than 24. Again, notice that our arrow in our alternative test is pointing to the right, and we are looking at the area to the right of our test statistic. A couple of things, depending on the author, the textbook of the study, you will it always will be, we call this the null hypothesis. H sub 0 is the null, but the alternative can be written as either HA or H1, and they mean the exact same thing. Then we have a two-tailed test where H0 is equal to mu, and the alternative is that HA is not equal to mu. So you might test the claim that the mean age of community college students is equal to a certain number, and then you just are saying, I don't think it's equal to 24. So that becomes a two-tailed test, and you look in the area of both tails of your test statistic. So you would take the absolute value. So if your test statistic was like negative 1.25, you would look over to the left of 1.25, negative 1.25, and to the right of 1.25. And I'm going to take a little check. Does anybody have any questions right now? Nope. You guys with me so far? Okay, great. Let's go back. All right, so again, this is just a bigger picture of what a right-tailed test is. So here we could test the claim that the mean is truly equal to 15, H naught mu equals 15, and we might want to claim that the mean is actually greater than 15 based on our data. This is again a left-tailed hypothesis test. The currently accepted mean is 5, and we might test the claim that the mean is actually less than 5. And that's just an extra picture. And this would be a picture of a two-tailed hypothesis test where the currently accepted mean is 50, and we're claiming that it's not equal to 50. All right, and then again here, they're just talking about p-values. This is a standard normal curve, and this negative 1.65 actually is the alpha 0.05. And our p-value is just the area to the left. So like the negative 2.085, that's the area to the left. So that's our p-value. And our level of significance alpha might be 0.05. Okay. Now, what we haven't talked about is what is it? How do we know whether or not to reject or fail to reject a claim? And if your calculated p-value is less than your level of significance, then you would reject H naught. If it's greater than your level of significance, you fail to reject H naught. And the question is really why. That p-value is the probability you would get that result if by chance, if that null hypothesis were actually true. So if you're getting a tiny, tiny, tiny little p-value, like a 0.0001 p-value, for that to actually happen, and then when the null hypothesis is true, that's a very small probability that that's going to actually be, the null hypothesis is going to be true and you're going to get that result. So if you have a large p-value, it's saying, okay, well, my p-value is like 0.75, well, yeah, there's a really good chance that my null hypothesis is true because 75 out of 100 times I'm going to get this result. Typically, alpha is usually set to 0.05, which if you think about our level of confidence goes with a 95% level of confidence, or our alpha would be 0.1, which refers to a 90% level of confidence, and things like that. So again, if your p-value is less than your alpha, you reject H naught. If it's greater than your alpha, you fail to reject H naught. All right, quick test, quick check. Questions? Okay. All right, so let's go back to our example here. We're going to test the claim that the mean is less than 16.43, okay? So we've got that our H naught mu is equal to 16.43, and our alternative is that mu is less than 16.43. And I would ask you to kind of write this down on a piece of paper. I'm going to jot this down because we're going to go to a different screen and we're not going to have this information in front of us. We also know that our mu is 16.43. And our x bar value is 16, our n is 19, and our standard deviation is 0.13. Okay, so I'm back in my statistical analysis spreadsheet. Remember that you have to go in, make sure that your Gmail account is open, and then go file, make a copy. This thing you only get read access to, and you can only put anything in if you've got your own copy. these little locks that's to keep you from being able to change any of my formulas. So on Professor Watt's sheet, sometimes these formulas got changed. You can't change these on my sheet. So let's go over to my newest sheet, which is hypothesis testing for the mean. And if you look right here, I haven't even, I clean that up. I'll clean that up real quick. I don't want to search that. I appreciate that, but all right. So first thing, we are doing what kind of test, guys? Left-tailed, right-tailed, or two-tailed test? Anybody there? Left. And I have a small sample size. It doesn't tell me that. I also didn't get any information about whether that standard deviation was the population or a sampled standard deviation, but my sample size is less than 30, so I'm going to go ahead and use the t-test. All right, so the first thing I do is I enter the mean, and that is 16.43. All right. And if you look down here, this will populate with what you put in for the mean, so you can test that it is what you want for the test. Because we did know that mu is equal to 16.43. We're testing mu is less than 16.43. Now we come down here, and you guys will put in the sample mean, which is 16. The sample standard deviation, which is 0.13, and your sample size, which is 19. Now look at that test statistic. My p-value is so small that I can't even, it doesn't even register. And also that t-statistic is way off there. So at the 0.05 level of significance, would I reject or fail to reject my null hypothesis? Yep, exactly right, Margaret. I would reject my null hypothesis. So hypothesis testing is just an extension of confidence intervals. We calculate this t-statistic the same way that we did in confidence intervals. It's your x bar minus your mean divided by your standard deviation divided by the square root of n. So we're just sort of repurposing confidence intervals in a slightly different form. All right, back to here. So again, here we would reject this claim. I didn't want to go to that page. Okay. Again, just some more examples. Here, example where my x bar is 286.2 and the mean is 275. We don't have to calculate anything, but it told me that my p-value is 0.1323. So at a 0.05 level of significance, 0.1323 is greater than 0.05, so here I would fail to reject my null hypothesis. Again, another example, my 65, my p-value is 0.0396, so it looks like it's a right-tailed test. We're testing the claim that the true mu is greater than 65. And I get a p-value of 0.0396. So at a 0.05 level of hypothesis, what should I do? Reject or fail to reject? You guys still there? Yes, reject. What? You're saying we should reject. Yes, we should reject because our p-value is what? Less than 0.05. So it's a very small probability that that would happen just due to chance if the if the null were true. Again, here this is showing you an example of a two-tailed test, and our p-value is going to be pretty big because the half a p-value is 0.27. So our p-value would be 0.5. We would probably reject. No, we can ignore that side. Ignore that side. All right, so this is an example that I'm going to show you both on the TI calculator and inside of the spreadsheet. So we have a whole bunch of data here. And if you are using, and that's not what I meant to do. If you are using the TI calculator, you go into L1 and you'd enter in all your data. Then you would look under stat, calc, I think it's tests, sort of the same thing. It's the same keystrokes you use for confidence intervals, and I'll quickly pull that up. Stat, calc, and you would go down to, you actually go to tests, and you would do t-test. And because we're putting in our data, we're going to use a one-sample t-test. And because we put our data in on a list, we choose data, list would be L1, frequency is 1, and we're testing the claim that the alternative is the right tail test is greater. So here it did all the work for us, and we got a p-value of 0.035. It's kind of telling us what all our summaries were, and at a 0.05 level of significance, we would reject H0. Okay, and they're also showing you a picture. Going back to our spreadsheet, here, I don't have one for list views, but I will add one, just like the confidence intervals with data, hypothesis testing with data. I'll add that sheet, and it will work just like this one. I thought I had added it. Okay. The other thing we need to discuss quickly is type 1 and type 2 errors. So when you're doing confidence hypothesis testing, you can make type 1 and type 2 errors. So just a little chart to kind of help us. Let's start with a type 1 error. So here we said decision is do not reject. This should actually say reject. Ah, you guys get to see that my thing is not perfect. I don't like using the Mac for this. All right. If we do not reject the null hypothesis and H0 is true, we've made the correct decision. If we reject H0, we do not reject H0, and the alternative was really true, we've made a type 2 error. If we reject the null hypothesis and it was actually true, we've made a type 1 error. And if we reject the null hypothesis and the alternative is true, we actually made the correct decision. I'm going to make this available after we're done talking, and there are 2 links on here which give you nice further explanations of the type 1 and type 2 errors. But if you use this chart and you're asked a question about what constitutes a type 1 versus a type 2 error, this is sort of a little shortcut for this. Your alpha level, like your 0.05, that is your level of significance, and that also drives the type 1 error. So if you think about it, if my level of significance, if my alpha is 0.05, that means 1 out of 20 times a type 1 error will usually occur. And that's just something to keep in mind. As this is an intro stat course, we're really kind of concerned with what is a type 1 versus what is a type 2 error. We don't get into power, we don't get into the beta, but we're just sort of need to be familiar with that. All right, so that's what I have in terms of my lecture on this subject. I'm going to stop recording now so that this can actually convert, and I'm going to open it up for questions.